We're starting this video on examples with the question, two cats are on a roof. Which cat is going to fall off the roof first? And the answer, of course, is the one with the smaller mew. You have a tilted surface, the cats are being held onto the roof by static friction, and the one with the smaller coefficient of static friction, mu sub s, is going to fall off first. Okay, here's an example of that that's a little more mathematical. Here we have a box on an inclined plane. The box has a weight of 50 newtons, and the inclined plane makes an angle of 30 degrees with the horizontal. We are going to analyze this problem in order to find the value of mu sub s, the minimum value that will keep the box from sliding down the ramp. So looking at this, the normal force is perpendicular to the surface, and there is a force parallel to the surface, which is what's going to tend to cause the box to slide down the ramp. We want the static frictional force to be at least large enough to balance that parallel force. So this guy here is Fs max. It needs to be at least this big. So if we can find the magnitude of the normal force and the magnitude of the force parallel to the surface, it should be straightforward to calculate the value of mu sub s. In this picture, you can see the lower right-hand corner here is drawn as a perpendicular, and the weight is always going to be perpendicular to the horizontal. So we have a couple of right triangles in this picture. The perpendicular to the surface is also perpendicular to the force parallel to the surface. So we have identified all of the right angles in our triangles in this picture. The angle in the upper left must be equal to 90 minus theta. And it must also be equal to the angle in the upper left of the small triangle, where we are finding the components of the weight. Which means this angle on the lower end of the small triangle must be equal to theta. And the normal force then must be equal to the cosine of theta times the weight, because the magnitude of the normal force is equal in magnitude but opposite in direction to the component of the weight that is perpendicular to the surface. And the parallel force must be equal to the magnitude of the weight times the sine of the angle theta. The parallel side is opposite angle theta. The normal force is adjacent to angle theta. So our formula will look like this. The normal force, W cosine theta, 50 newtons times cosine 30 degrees is 43.3 newtons. The parallel component is going to be 50 newtons times sine theta, which is going to be 25 newtons. So we know the parallel force must be equal to Fs max, and the normal force is equal to N, right, the normal force. So our formula, Fs max, is equal to mu s times N. So we can rearrange that and plug in the knowns, and we get mu s must be at least equal, so you could also write this as greater than or equal to F parallel divided by N. 25 newtons is F parallel, 43.3 newtons is N, and our newtons cancel, giving us a mu s of at least 0.58. Notice that the 0.58 is dimensionless because it's the ratio of two forces, so it has no unit associated with it. It is a ratio. Now we're going to find the forces on each end, which we will label F left and F right, for a bridge. F left and F right. We have a 1,000-kilogram car going across the bridge. At this point, it is 5 meters from the left end. The bridge is uniform and 20 meters long, so the mass of the bridge is going to act like it is at the geometric center of the bridge, and the mass of the bridge is 500 kilograms. So we need to write two equations. We need to write an equilibrium equation for the force, and we need to write an equilibrium equation for the torques. The equilibrium equation for the forces is going to all be in the y direction because from the diagram we can assume that the horizontal forces, both in and out of the page and left and right on the page, are equal to 0. So we have the forces, the mass of the bridge times the acceleration due to gravity, and for the purposes here we're going to call that 10, and the mass of the bridge times the acceleration of gravity, little g, and again for purposes of making this calculation easy we're going to call that 10 as well, and therefore our force equilibrium condition is that negative 15,000, the weight pointing downwards, has to be equal to the sum of the force on the left-hand end of the bridge plus the force of the right-hand end of the bridge, and that is our force equation. We need a torque equation, and there are actually two separate torque equations that could be written to describe this bridge. We're going to find the torque about the left end of the bridge, so we're going to assign what's called the axis of rotation to be over here on the left end of the bridge. And then we're going to find all of the torques about the left end of the bridge. In order to be in equilibrium, the sum of the torques must be equal to 0. So we have the torque generated by the weight of the car, which is going to be 1,000 kilograms times 10 meters per second squared, or 10,000 newtons, times 5 meters. F times r. Theta and r make a 90-degree angle. Sine of 90 is 1, so we can leave that out. There's an assumed 1 here. The mass of the bridge is 5,000 kilograms, so the weight of the bridge is 5,000 newtons. And it acts at the center of the bridge, so the lever arm for the center of the bridge is going to be 10 newtons. Or 10 meters, I'm sorry. I don't want to restart for that mistake. 10 meters. And the force on the right-hand side of the bridge is exerting a counterclockwise torque, so it is positive. The first two torques were clockwise, so we assign them negative signs. And we have the force on the right-hand end of the bridge, which is one of the things we're looking for, times 20 meters. And I want to point out that the torque due to the force on the left-hand side of the bridge, where our axis of rotation is going to be a radius of 0 meters times our force, and therefore that left-hand torque, that torque created by the left-hand force, about that axis of rotation is going to be equal to 0. We could have done the same analysis about any point on the bridge, because if the bridge is truly in equilibrium, the torques about every point must be 0. But we choose this left-hand one because it's convenient. So the force on the right side is the sum of negative 5,000 times 10 plus negative 10,000 times 5, which gives us 100,000, divided by 20. When you do the algebra, right, you move that to the other side, that becomes positive. Move that to the other side, that becomes positive. And you divide by 20, so you have 100,000 divided by 20, which is 5,000. So our rightward force, our force on the right, is 5,000 newtons. Then we could either create a torque equation about the right-hand side. In other words, we could put a second axis of rotation here and do another torque equation, or we can just plug it into our force equation over here, which we have already established. And that would give us that the force on the left-hand side is 15,000 minus the force on the right-hand side, which we calculated to be 5,000 newtons. So the force on the left-hand side is 10,000 newtons. If you look at this for a second, there is a certain logic to that. Since the car is closer to the left side than it is to the right side, you would expect the force to be greater on the left side than it is on the right side. And that's the end of this example. There are some homework problems associated with this material, which we will certainly look at in the future. And this equilibrium set of problems is actually very important for some biological examples that we'll look at. And don't forget, there were pictures of kittens in this, so you can't be unhappy.